for this computer. Okay, what about that? Okay, can you just agree to that?
That's not actually on the screen.
Okay, welcome again. Today we have another episode of FSI Semianr Series. We are showcasing regional diversity in space research. And today we have Dr. Kerri, Donaldson, Hanna from UCF Physics Department. And the topic for today will be Lunar-VISE, V-I-S-E, an investigation of the moon's non-mare silicic volcanism at the Gruithuisen, how to pronounce this very hard word, Gruithuisen Domes. A little more about today's presenters. Dr. Donaldson Hanna received her BS in Space Sciences at Florida Institute of Technology and her MS and PhD in Geological Sciences at Brown University. And she did a postdoc at the University of Oxford, where she received UK Space Science RMS Research Fellow. And she's the assistant professor at UCF Physics since 2019. Her research group focuses on better understanding of the formation and evolution of earless bodies, their distribution and behavior. Now, please take it away. The time is yours.
Yeah, thank you for that introduction. Okay, so today I'm going to be talking about Lunar-VISE, or long way of saying is the Lunar Vulkan Imaging and Spectroscopy Explorer. For those of you that may not have heard, back in June of 2022, UCF was selected to lead a mission to the Gruithuisen Domes. And so myself and Dr. Addie Dove organized and led the mission. Mission proposal to send a rover and lander payload suite to these two features that we're looking at in the image here. And so today I'm going to be talking about that. But before I do that, I thought I would give some context of the PRISM, the NASA PRISM program. That's how we were selected, and also the Commercial Lunar Payload Services program through NASA as well. So much of this work and kind of ramp up to getting instruments and experiments and rover and technology at the lunar surface is really driven by the Artemis program. And I'm sure most of you have already seen this slide, and this has been beaten over your head of what the Artemis phase 1 path to the lunar surface looks like. And of course, when we look at this image, while everything in the image and the trajectory of getting astronauts to the lunar surface is still on track, we just have to remember that the timeline isn't necessarily on track. But leading up to getting human presence at the lunar surface, we are going to start preparing and better understanding the lunar surface using suites of instrument payloads on rovers and landers. And this is all done through this here, which is the CLPS program, or the Commercial Lunar Payload Services program. And so what the CLPS program is essentially a mechanism for working with aerospace companies to get payloads to the lunar surface and to start building the lunar economy. And so eventually what the purpose of the Commercial Lunar Payload Services program is to get a thriving economy so that anyone that has a payload and has money can pay one of these providers some whatever amount to get their payload to the surface of the moon. To get this going, NASA has started soliciting PRISM package payloads for science investigations, and they've started buying those initial payloads or amounts of masses on these landers and rovers. Now you can see here that this is an initial list of CLPS providers. I have pared this down a little bit because as we found out, the lunar economy is very enigmatic and space is hard. And so several of the CLPS providers have already gone bankrupt or are no longer existing. So Aston Space was on here, a couple of others. But what we see here are aerospace companies that are or currently or planning in the near future to be building rovers and landers to go to the lunar surface. So as I mentioned, NASA is the first customer on these CLPS program landers and rovers. And again, this is a mechanism for NASA to start building up the lunar economy. And so if you would like a payload on a lander or a rover, you can solicit your ideas or propose your ideas through the PRISM program, which stands for Payloads on the Surface of the Moon. And these are proposals that should be science driven. And so you have to have a science question and a science investigation. And then you have instruments that you select that can uniquely address that science question. You can have technology development payloads as part of your science package. And so if you wanted to have a dust collector, or if you wanted to test some new technology, it can definitely be proposed as part of your package, but it can't be the main driving thrust. Really, this is not exploration monies, this is science investigations. And NASA has now had 2 calls through the PRISM program. And there have been 4 selections from those 2 PRISM calls. The first PRISM call, there was landing site selected at a lunar swirl, which is Raynor Gamma, and a payload from Johns Hopkins Applied Laboratory was selected, Lunar Vertex. They also selected Schrodinger Basin as a landing site. So this is going to be on the far side of the moon in South Pole Aitken Basin. And a suite of instruments has been selected, specifically looking at the seismic activity and looking at lunar interior temperatures. And then in the PRISM 2 call, they identified 2 landing sites, the Gruithuisen Domes, which is where we propose to, and then also South Pole, so somewhere in the South Pole. And they selected an instrument suite going there. There's also been a PRISM 3 call already out. And so these have been released on kind of an annual basis now, which is fairly rough if you're continually applying to them. But they've been having an announcement about once a year. And in the PRISM 3 call, you could actually designate where on the lunar surface you wanted to go. So you could actually pick anywhere on the moon that you wanted to go, as long as it was plus or minus 70 degrees from the equator. And you had access to a lander and a rover, and also survive the night capabilities. One of the things that the early mission calls did not have were survive the night capabilities. So for our mission, we are not anticipating having to survive the night, although I'm guessing that we'll try to see if the instruments will survive, but there's no requirement for that to happen. And so, yeah, we'll be talking about the Gruithuisen Domes. When we look at where we're going to be exploring on the lunar surface through these PRISM calls, along with the CLPS program, here is a map that's pretty outdated now, but this was the planned deliveries for 2022 to 2026. And now this map looks a lot different. And so we've had some missions or CLPS landers altogether just go away. And so the Maston lander to the South Pole of the Moon has been canceled altogether. And so instruments that were on that payload have been repurposed to other landers. So those scientists will still get their data collected. And then we've also had things shift locations and also shift time. And so as an example, this is showing Viper that's going to be delivered through the CLPS program. That's now anticipated to be November 2024. And then the first 2, the other 2 landings will be in January, both probably in mid-January. So Intuitive Machines is looking to land in Mare PRISM in mid 2023, so in June. And then Astrobotic has the Peregrine lander that will also, it was supposed to already be launched, but it'll be going in mid-2023 as well, is the anticipation. They've also moved the landing site for this mission to actually the mare material surrounding the Gruithuisen Domes. And so we'll be getting data from the mare surrounding the domes before we get there from this other lander. And so, and then here's us here at the Gruithuisen Domes in 2026. So you might wonder, why do we care about the Gruithuisen Domes? Why did NASA select the Gruithuisen Domes as a location to send a rover and a lander payload to? And it really goes back to even the 70s and 80s when we first started getting telescopic observations of the domes. And so if we were going to orient ourselves to where the domes are on the moon, here's an image of the near side of the moon, and this circle here is the Gruithuisen Dome area. Using telescopic data back in the 70s, when they looked at this area of the moon, they identified, at least at ultraviolet wavelengths, that these domes stood out from their surrounding materials. And so they had a very steep red slope at ultraviolet wavelengths, meaning the reflectance increased as a function of wavelengths. And so they really stuck out from everything surrounding them. And so that in itself was an indication that these are unique features and there must be something about them that's making them different. And so then using imaging data, looking at the domes, they noticed that they had very steep slopes and very flat surfaces. So when we look at the mare, which are all that volcanic flows surrounding it, for the mare to be this flat and have flowed across a large plain, the viscosity of that melt must have been really low, meaning it could flow like water very easily across the lunar surface to fill in the basins. But when we look at these features here, the domes themselves, that lava did not flow very far before it solidified, meaning its viscosity was really high. And one thing that can increase the viscosity of any magma is the silica content. And so just by looking at how small the features were and how steep the slopes were and how flat the surfaces were, they said, okay, this melt or this magma must have been really, really silica rich. Now, that begs the question, we don't see these everywhere on the moon. And so these are fairly unique features. There's maybe a handful of features similar to this. And so when we see anything on any planetary surface that's kind of unique in nature, we think, what on earth would create this type of material? And so when we look at Earth as an analog, where we see these highly silicic magmas are usually in areas where we have plate tectonics and water. And so in areas where you have one continental tectonic plate subducting under the other, dragging water into the interior, and that water helps heat the magma in the interior and create a volcano. And so as an example, Mount St. Helens is one of these types of craters, or one of these types of volcanoes. Now, if you know anything about the moon does not have plate tectonics, and it also does not have vast amounts of water. And so that means whatever process that is creating these features on the moon has to be very different than what's creating them on Earth. And that in itself makes it really intriguing as to how these features got there. After those early telescopic observations, we had remote sensing observations that also looked at these areas. And we noticed a couple of things. We noticed that they were enriched in thorium, which is a heat producing element. When we look at the lunar surface, we only see heavy concentrations of heat producing elements on the near side. And in particular on the gamma dome, it seems to be highly elevated in thorium. So that's kind of intriguing. We also see that these areas are low in iron. And these are all came from lunar cross-spectral data. And then once we started getting diviner observations of the lunar surface, which is looking at thermal infrared wavelengths, we saw that their thermal infrared spectrum was very different from the surrounding materials. You can see that they're very blue compared to the surrounding red of the mare. And so this was suggesting or confirming the idea that these were highly silicic. And then we also see that the regolith covering these domes have a very different thermal inertia than the surrounding materials, meaning the rock properties on top of the domes appear to be different than the rock properties in the mare below. And so all of these things point to a very intriguing place for us to go because we want to understand how do we get these types of rocks on the lunar surface, and can we use what we know about the technical properties of the regolith at the domes help us drive technology development? Can it help us build rover wheels and drills and better understand how to explore the lunar surface by studying these different regolith properties of the domes? And so we proposed a science investigation of trying to understand how silicic volcanism works at the Gruithuisen Domes, and then how can we use that information at this one location and apply it to the other handful of silicic volcanoes that we see on the moon. But you know, it being at UCF, we also wanted to make sure that we had an exploration goal. And so not only do we have our science investigation, but we also have an exploration investigation where we want to understand the geotechnical properties of the lunar regolith at the Gruithuisen Domes and how we can then apply that to other areas that appear to have this lower thermal inertia qualities. So our lander payload includes a suite of Ball aerospace cameras that draw heritage from some of the cameras that Ball Aerospace has developed for Earth studies. And so in particular, we're going to be using their geospace camera. And so we'll have 2 of these cameras on the lander. One of the cameras will be a descent camera, so we'll be looking directly below the lunar lander. And so as we approach our landing site, we'll be able to image and map the landing area so that we'll be able to assess where we want to drive the rover. And it'll also image how the plume interacts with the regolith, which will also give us a better understanding of the regolith properties and how plume interactions might change between the material on top of the dome versus what they'll see in the mare. We'll also be using a Ball camera to be a context camera. And so the context camera will be mounted on top of the lander. It'll have the capabilities of scanning 270 degrees. And so that will allow us to characterize our landing site, help us pick the traverses the rover is going to make. And it'll also give us the opportunity to take movies of the rover as it's interacting with the regolith. And that will allow us to see how, as the wheels are spinning, or if we're asking the rover to dig a trench with its wheels, how dust gets lofted and how long that dust stays lofted. And so that is our package of instruments on, yeah, Tyler.
So what would the frame rate be for these cameras?
Yeah,
Like,
so,
like how precise would you be able to film?
yeah, so we have movie capabilities of 5 frames per second while we're descending. And we won't be collecting 5 frames per second through the whole descent path. And this is actually something that Addie was calculating just the other day. We were looking at other trajectories like the recent Chinese landers and trying to see what their paths are, because if you collect 5 frames per second, as soon as the moon comes in to the scene of your camera, we calculated it would be like, I don't know, 10,000 images or something, which is unreal. And we also don't have space for that. So we're going to have to change our cadence where in the beginning, we'll only be collecting data probably once every like 10 minutes. And then when we get to a certain altitude, we'll transition to taking once a minute And then when we're about 40 to 50 meters off the surface, that's when we'll go into the movie frame rate and collect 5 frames per second. And then for the context cameras, it's the same exact camera. So we'll be also able to collect 5 frames per second. So not like super high frame rate, but good enough for these initial studies. And then on our rover, we have a suite of instruments that include multi-spectral cameras, and then also a gamma ray and neutron spectrometer. And so we have a multi-spectral visible and near-infrared imaging camera that we call LV-VIC. And so this is essentially the same exact camera that's going to be on our lander as our context camera. The only difference is that we're going to be applying spectral filters to that camera so that we can do some spectroscopy. We've even considered taking 2 of those channels, spectral channels, and turning them into polarization channels so that we can potentially get polarization measurements at the surface as well. So we're still doing a trade study on whether or not we'll do the only spectral channels or have some polarization capabilities. But we'll use that visible near-infrared camera for looking at variations in composition across the dome as we're traversing with the rover. And we'll also be looking at just rock textures and morphologies, because just looking at the rock texture alone can tell us about what type of volcanism is occurring on the dome. We also have a multi-spectral thermal infrared system. This system is based on a mid-infrared or a thermal infrared radiometer that was supposed to go to the south pole of the moon on that Maston lander that went bankrupt. And so we were supposed to have heritage with that instrument that was going to go to the south pole of the moon. But now it's very likely that that thermal infrared camera is actually going to be launched after our camera. And so it won't have heritage on us, but this is an image of that camera already built. And so it's just going to go sit on a shelf until it goes to the surface in probably 2026 or 2027. But using the thermal infrared camera, we can look at composition. So we can really constrain the silica content of rocks using the thermal infrared. And also very importantly, we can use it to understand the thermal physical properties of the rocks and the regolith. So we can look at thermal inertia, we can look at porosity, we can look at how compact the regolith is. We can do comparisons between the fluffy in situ regolith versus what we've driven our rover over to see how packing the surface changes the thermal properties. So the thermal properties will really come into play not only with the science investigation, but also our exploration goals. And then we also have a gamma ray and neutron spectrometer that's on the rover that's going to be looking at mapping elemental abundances. So this is going to be looking at heat producing elements like thorium and potassium and uranium, but also the major element species like iron and magnesium and silicon. And if there's elevated abundances of hydrogen, we should be able to detect that as well. And this instrument also has heritage from Arizona State University. There's a mini neutron spectrometer on the Luna mission. It was the small simplex mission that was launched as part of Artemis 1. And so some of you may have heard of it, may have not. It was launched. Unfortunately, they have not been able to engage the boosters or the thrusters on the spacecraft. And so it's been making very large orbits around Earth and Moon, but it's because it cannot turn on its thrusters. It can't actually go into lunar orbit right now. And so they keep trying to see if they can get the thrusters on. And the instrument itself is actually working. And so when it does fly by the moon, it does actually measure neutrons coming off. And so they've gotten a really beautiful signal, the neutron signal coming off the moon. But unfortunately, they haven't been doing their science. They haven't been able to do their science investigation in the way that they wanted. Okay, so on the rover, we are going to mount both of our multispectral cameras in a single enclosure to make it very simplified and straightforward. And so on top of the rover, we'll have a single enclosure, which includes the visible near-infrared multispectral camera and the thermal infrared spectral camera. And so that will allow us to point the two cameras at the same exact location on the lunar surface, so that we'll get visible near-infrared and thermal infrared data for anywhere that we look. We will, if we're about a meter off of the surface of the, if we're about a meter off the surface, we'll see about 3.6 meters in front of our rover. And at that distance, we'll have a spatial resolution of less than 1 centimeter. And so this will be really great spatial resolution for looking at fine details of rocks and regolith as we're roving about. And then our field of view will extend all the way up to 2 degrees above the horizon. And so we should be able to see near field and also into the far field. The cameras are also on a actuator, and so we can rotate both camera systems, and so that we can make a 180-degree panoramic scan. And so essentially, as we're rotating the cameras, a different filter will come into place and we'll build up multispectral capabilities of each area that we're looking at. So similar to what we're looking at here, where we see this at one wavelength and then the next wavelength. And then we will have a gamma ray and neutron spectrometer. The gamma ray and neutron spectrometer is very sensitive to all materials around it. And so we actually want to limit what it's interacting with. We don't want a signal coming off of the rover or anything nearby. And so we are going to have to mount that as far away from our camera system and at the bottom of the rover, so that it's mostly just looking at the surface and collecting gamma rays and neutrons just off the surface. And you might say, well, wait a second, why do you have this like really silly drawing of a rover? And it's because we don't actually have a rover yet. And so one of the things that I failed to mention when I was talking about how PRISM and CLPS work together is that your payload is selected first, and then you work with NASA to identify all your requirements for your payloads to be successful at the moon. They then create an announcement of an opportunity for the CLPS providers, and then the CLPS providers bid to build your lander and rover. And so we're currently in the process of creating our appendix of requirements, and so we don't have a rover yet. And so we just, for the proposal process, just put in this very silly diagram, just illustrating what we needed it to do. Okay, so as I mentioned, this is a science-driven mission, and that is what PRISM is supposed to be, is a science investigation at the lunar surface. And the key questions that we really want to address at the Gruithuisen Domes is what the composition of the rocks are, because that is what we don't know. From orbital data sets, we have hints at what those rocks are made out of, but we haven't had the data yet at the spatial resolution that we need to really understand the real composition of the rocks. And so we will be using our rover payload to look at variations in composition across the dome as we're traversing. And we want to be able to correlate anything that we see with composition to any rocks, regolith, any surface features, or any dome morphologies. And so again, we'll be doing that with a suite of our instruments. And so with the thermal infrared camera, we have the spectral capabilities of mapping a feature that we call the Christensen feature. And the Christensen feature is a thermal infrared spectral feature that's indicative of composition. And so just by measuring that feature, we can then assess how much silica and other materials are in a rock. And so this plot here is just showing that if you know the Christensen feature position, then it gives you an idea of how much silica you have in that rock compared to silica plus calcium plus iron plus magnesium. And so you can, if we had a big complex diagram of all the rock types, we can pull out each rock type based on that CF position. And so that's what we're really trying to do. But the really great thing about our payload is we have multiple ways of doing things. And so while we will be using the thermal infrared camera to understand the composition or the silicic, or how much silica is in the rocks, we can also get that with the gamma ray and neutron spectrometer. And so the gamma ray and neutron spectrometer will give us an independent measurement of the silica, and then also give us other things like iron and magnesium. And so we'll have two ways of looking at composition. And then we'll also be detecting thorium with the gamma ray neutron spectrometer, which will allow us to test different formation hypotheses. Another thing that we want to make sure to do is we want to be able to ground truth all the orbital data sets that we currently have in hand. We actually have a wealth of data from the moon, but it's all from orbit. And so having surface measurements that are as similar to the orbital data as possible allows us to make that really critical link between what we're seeing at the surface to what we're seeing from orbit. And so for both of our cameras, we have chosen spectral channels that overlap or coincide with other spectral channels on other data sets. And so as an example, at the visible and near infrared, we've already had orbital data from Clementine, from the Kaguya spacecraft, as well as the Lunar Reconnaissance Orbiter camera. And they all had spectral channels listed here. And so we're trying to mimic or replicate all of those spectral channels as close to as we can, so that again, any measurement that we make at the surface with a rover can be directly compared to what we're seeing in orbit. And then at the thermal infrared, we've had data from the Diviner instrument. We would have had I should be optimistic. We still may have measurements at the South Pole from L-Cirrus, which is the thermal camera that's going to go to the South Pole of the moon. And then in October, there's a small sat that's going to be launching called Lunar Trailblazer. And Lunar Trailblazer is going to have a thermal camera on it with several spectral channels on it. And so we've selected for Lunar-VISE 3 channels that overlap both Lunar Trailblazer data as well as Diviner data. And so again, we'll be able to make that critical link at thermal infrared wavelengths from the surface to the orbital data. And of course, we've also had gamma ray and neutron spectral measurements from orbital measurements from Lunar Prospector and Kaguya that will be able to link surface observations with orbital data. And as I mentioned, one of the key components for any geologist is really trying to understand what on the surface is giving you these spectral signatures. Like, spectra is really important, but the context of where that's coming from is also equally important. And so as we're roving about, we'll be using the imaging capabilities to make sure that we get really great images of rocks on top of the dome, as well as regolith, because we want to study both. And then we can relate that to any thermal properties of those rocks and regolith. And in particular, we're really interested in understanding how porosity is expressed in the rocks, as well as the regolith, and how that plays into the thermal inertia of those materials. And again, this will be really critical for helping us understand the Diviner data that we're getting from orbit. As I mentioned, we also, not only do we have a science investigation goal, but we do have an exploration goal, and that is really to understand what the variations of the regolith are across the dome, and how the regolith behaves both with the rover and the lander itself. And so similar to investigations that we've seen with Apollo and with the U-22 rovers, as well as some of the other landers, we want to be able to characterize how much of the surface is being disturbed as the lander is landing, We want to be able to see how much of the regolith is disturbed as our rover is moving about. Now, obviously, this is a huge rover with humans on it. And so we probably are not going to kick up the amount of dust that are in these images. We're just crossing our fingers that we get some amount of dust lofting that we can see, but well, you know, we don't know, and that's not a requirement that we can put on the rover is must be able to kick up dust. But we're hoping that we'll be able to see that and record that so that we can better understand the dust and the regolith properties. And then, of course, you know, it'll be really important as the rover is traversing the dome is to go back and make sure we're first measuring or getting images and spectra of undisturbed regolith, but then turning around and looking at the disturbed regolith to see, you know, what compressing and interacting with the surface does to the spectral properties. And we're certainly hoping that while we can't put requirements saying that the rover has to create dust, we can actually say that we want the rover to be able to create a trench or something. And then we can study things with depth and then also, again, see how things are disturbed, see how the angle of repose changes or what the angle of repose of our trenches look like and how that affects the geotechnical properties. So what are we currently doing now? Other than having lots of meetings and talking about budgets. Basically, we've been going through and we're doing that really onerous task of going through and identifying everything that we're going to need from the rover and from the lander to be successful on the moon. And so that's, you know, how high off of the lunar surface do we want our instrument to be? Now, obviously, we can't say we want it exactly at 1.0 meters off the surface. We have to give them a range. So we're assessing how big the boulders are and the average boulders that we're going to be seeing because we want to be able to see over them. Or we at least want our antenna to be high enough above the boulders because the communication that we're going to have is all line of sight. And so if we lose any line of sight with the lander at any point in time, the rover will not know where or won't know what to do because it can't communicate. And so, yeah, we're going through painstaking details about everything that we need from the lander and the rover. And that also includes selecting a landing site on the domes itself and creating a concept of operations for the 10-day mission that we're going to have. So what are the waypoints that we want to go to? What do we want to do at each one of these waypoints? How long it's going to take to each measurement. And so we're really fleshing that out because that also will go into our Appendix A. Speaking of landing sites, we did actually propose to land on top of the dome. The only requirement in the announcement of opportunity said that you had to be able to land on a relatively flat slope. And luckily, the tops of the domes are very flat. And so what we're looking at here on the left is a slope map. And so anything that's blue is less than, well, it's on the order of like 0 to 4 degrees in slope. And so all the tops of both of the volcanic domes meet that requirement. And so we thought, well, we should propose to go to the top of the dome if the only requirement is that it has to be flat. And so we initially assessed 2 areas this is the Gamma Dome, this is the Delta Dome. And in particular, the area that we've been focusing the most on is this part of the Gamma Dome here, which is really close to a small crater. And so if we zoom in to this part of the Gamma Dome, this is what we see. And this very small crater, you know, because this diameter of this crater is only probably 100 meters across, but it's created a huge density of boulders on the side. And it's a very fresh crater. And so if you zoom in, you can see those boulders here. It might be hard to see in this image, but a colleague of mine has started doing boulder counts, and there's like thousands of boulders in this very small area. And so we're looking at various options within this area that we could land and then safely traverse over to the boulder field to take images. And then we also want to be able to go as close to the edge as we can, so that we can look down at the surrounding mare and get measurements of it as well. Of course, this was before like we really started looking at it. So this is what we had in our proposal of how beautiful it looked. But then we started really looking at it and started really trying to understand the surface. And so this is a topographic map here. And again, this is the area that we're looking at, which looks like this from an oblique angle. And so you can actually see that there's actually different little plateaus here. That when we start thinking about where our line of sight communications is going to still be able to work, and we can still rove and do our science, really may limit where we're going to be. So we've been doing a lot of analyses of slopes and view sheds to really understand if we land maybe up on this flatter surface here, how far can we traverse down and before the slope gets too steep. And so we've been doing all these assessments where, yeah, we've been looking at slopes. And so if you just look at the more detailed slope map, everywhere that's gray has slopes less than 5 degrees. And so we need a landing ellipse of 100 meters in diameter to identify, and we need those slopes in that 100-meter diameter, a landing ellipse. So we've been looking at that. Everywhere that's pink or dark red, those are slopes that we probably can't traverse. Now that isn't because the companies have told us they can't traverse it, but we've been told that that's how we need to assess it. And so we've been taking that information and starting to look at different view sheds, meaning if we were to land at this landing site and we assume that our lander is at 2 meters in height and our rover is at 1 meter in height, where can we actually traverse that the rover and the lander can stay in line of sight? And so we've been assessing that for different parts of that little plateau so that we can see where we would be able to traverse. And so here, if we landed in this landing ellipse, we would be able to traverse anywhere that's green. And we would still have line of sight communications with the lander. In this image, if we land in this part, this gives the green tells us where we can traverse, and then this is if we landed here, and this is if we landed here. And so we can immediately start realizing, okay, well, this isn't a great landing site because we can't get down to the boulder field at all. But we've now been looking at these 3 landing sites here on the bottom, because each one of these gives us access to where we can, without going on an aggressive slope, get down to the boulder field. And so right now we're working on counting all the craters, the very small craters, so things on the scale like 1 to 2 meters in diameter and above. In each one of these landing ellipses, we've been counting boulders in every single one of these landing ellipses, and we've been calculating the terrain ruggedness to basically see which of these sites might be safest for us to land in. Okay, and with that, I'll get to my summary slide. Lunar-VISE is the main science goal, really, is to go to the Gruithuisen Domes and understand the composition and the rock type that is comprising the Gruithuisen Domes. And being able to do that would really address the major outstanding question about that specific geologic location on the lunar surface. And having that silica content, both from thermal infrared spectroscopy and gamma ray and neutron spectroscopy, would allow us to really test the formation hypotheses that have been put forward for the features. We're going to have 10-day science investigation, and we purposefully proposed a very straightforward rover and lander operation investigation to show that this was actually possible at the lunar surface. Because that is one thing that they evaluate. You don't want to propose this pie in the sky of like, we're going to have 500 instruments and we're going to have all this time. And we're going to take all these measurements. We went through and made sure that it really was possible to address our science goals in those 10 days, even with margin, to really give them confidence that we would succeed. And yeah, I mean, we're really looking forward to collecting the data and maybe getting some sleep in 5 years when this is all over. And so with that, I'll take any questions that you have. Thank you.
All right. Go ahead.
About what margin are you working on?
Cost margin, mass margin.
Sorry, time wise, you said you can accomplish your science goals in 10 days, but there's a margin, so I assume that means you can accomplish them in less if needed.
Yeah, so I mean, we could accomplish our science goals in probably 3 days. Because depending upon where we landed, and that's assuming we make a single measurement of a boulder and the regolith. And that would address our science goals because we would have a measurement of a rock and would have a measurement of the regolith, and that would give us composition. And having 3 days would give us enough time that we could make sure that we're driving outside of the disturbed zone, because while we want to characterize the regolith within the disturbed zone from the landing area, we want to make sure that we get outside of that disturbed zone because we want to study the in situ regolith and rock. And so we do need time to be able to go out there.
Okay. Online viewers, please unmute yourself if you have any questions.
If you survive a lunar night, would you further your science goals, or would you is there like a subset that you have like a just in case, like we can also do these without extra things?
So we would have to, if we survive the lunar night, we would probably have to ask NASA if they would give us additional funds to operate.
Yeah.
They are actually only paying the lander and rover provider to have a lunar day. And so it would then be up to the lander provider and rover provider to still want to operate, and whether or not NASA would give us funds or if they would be willing to like let us still do things. But we haven't even, yeah, we're so like in the weeds of like trying to appendix A that we haven't even thought about the possibilities of like surviving the night. But I mean, what we'd really like to do is keep the cameras on the rover on as long as we possibly can, and that they will transmit data back, because as the sun goes down and everything starts cooling off, the thermal camera will still be able to collect data, and it will be really valuable data. And obviously we also want to use the context cameras and point them to the horizon, and so that as the sun is setting, try to get any horizon glow from dust that's lofting in the electrostatic environment at the horizon. And so we're going to leave them on in hopes that we'll get those measurements, but we did not put them in as requirements because we just don't know if we'll get them.
Sorry. I know you say you don't have a rover yet, nor have going over requirements, as you say, you're going to do that there with NASA itself. But I was just curious in the stuff that you did have, that you had some sort of radiator. Like, I was just curious what is the specific reason what it's for.
Yeah, so for the lunar environment, you have to remember that there's no atmosphere to temper solar radiation. And so when the sun is hitting the surface, it is really hot. And so at lunar noontime, we're expecting temperatures on the order of 390 Kelvin because we don't have an atmosphere. Now, most instruments won't survive 390 Kelvin. And so any instrument is rated to survive some, very small temperature range. And so the radiator will have both a heater and a radiator. The heater will keep us warm on the way to the moon because it'll be really cold in space. And so we want to keep the instruments healthy on the way there. And then we should be landing close to lunar dawn or just after dawn, so it still may be too cold. So we may need the heaters then. But then when the sun rises, the radiator itself will actually absorb and re-radiate the energy back out to keep our instruments at the operating temperatures that they need to be. And so essentially, all of our instruments will need one for the multi-spectral cameras on the rover. We'll need one for the gamma ray and neutron spectrometer. We'll actually probably need it for the electronics boxes. Yeah, so this is another thing that actually the ball group is calculating is where we need radiators and how big they need to be and where they need to be and all those sorts of things.
Thank you very much.
Yeah.
I'm assuming that for electric power, you'd be looking into you getting away from solar, or maybe some.
No, so it will be most likely solar power. And so we've been told that the landers will most likely use almost up all of their energy just getting us to the lunar surface. And then our science investigation is supposed to be 10 days, but we will probably be on the lunar surface closer to 12 to 14 days. And that's because the first 2 days after landing will be them pulling out solar panels and charging. And the other thing that we have to consider when we're thinking about concept of operations is that the rover can't just drive 24 hours a day. It also will need to sit and charge. And so we've been told that we could assume that we're operating 16 hours a day and that we might need to 16 hours an Earth day. And that we should assume that we might need 8 hours of Earth time to charge. And so we have to also keep that into account when we're thinking about how far we're driving, how long we're taking measurements, because they'll be controlled by how long the rover can stay powered for.
And those are just metrics that they just provide you, they don't really tell you why or.
Yeah.
Okay.
So, yeah,
I was just
so,
curious.
so we have a Commercial Lunar Payload Services integration manager, and her job is basically to be the interface between us as a team and all the CLPS providers. And so she's very in tune with what the landers and the rovers' current capabilities are. And she tells us, well, here's what the current capabilities are. And so if any of these companies bid to put you on the moon, you could expect these things. Now we can ask for more if we think we need more of anything, or like if there's not current technologies to do something, we can ask for that. They can't guarantee that they'll give it, especially if it's going to cost a lot of money.
Right.
And so our expectations and our requirements, we have to make sure that we get what we need, but don't ask for so much that it starts becoming too expensive.
Thank you very much.
Yeah, thanks.
Okay, any more questions? Yeah, I think then it's time to conclude. Let's thank our sponsor again.